Welcome to GetXAIML. In this video, we'll understand the concept of dimensionality reduction and principal component analysis with mathematical intuition and the examples. Now, what is this dimensionality reduction? Why we need it? So let us understand the curse of dimensionality. If the data is too many dimensioned, okay. So for example, say that if I give you one dimension data, you can just see it on a straight line. Two dimensional in a plane, three dimensional, you can see it as a cube. For example, it's given in the figure here. So if I give you 10 dimensional data, 20 dimensional data, so it becomes difficult to visualize. Okay? Difficult to visualize and find the patterns. That is one thing. Second thing is, it will be when you process the data, it will be computationally intensive. Okay? Computational intensive means it will take a lot of resources in my computer and time as well. So for that reason, we need to reduce the data. That is the curse of dimensionality. It may have unwanted data also, unwanted patterns. We don't want that. Okay? We call it as noise or redundancy. We have to remove that. Then if you do all these things, definitely our machine learning algorithms will improve in terms of performance and accuracy. So to remove the curse of dimensionality, the plan is you reduce the dimensionality to lower dimensions, higher dimensions to lower dimension. For example, in the linear discriminant analysis, we have done it, right? So check out my video on linear discriminant analysis. That is also a dimensionality reduction technique, but that is a supervised machine learning algorithm. Here we are going to learn about the unsupervised machine learning algorithm, that is PCA. So what is the curse of dimensionality in short? As dimensions increases, data becomes sparse. Distance metrics lose the meaning. Okay, a lot of data, a lot of features, and computational complexity rises. So what is the idea here? Dimensional reduction. So for example, say that I have a three-dimensional data. Okay, assume that it is having the curse of dimensionality. That is, it is difficult to process and visualize and find the patterns. Can I reduce this into a two-dimensional plane like this to easily visualize that? Can it further be reduced to one-dimensional line like this, so that the computational intensity reduces and the performance of the machine learning algorithm increases? That is the goal of the dimensionality reduction. So one of the popular algorithm is unsupervised learning algorithm called principal component analysis, which is the dimensionality reduction algorithms. Why we need this? So again, the same thing. Problems in high dimensional data is it leads to overfitting of your data. So that means what? The model becomes too complex. It requires high computation. So that is the curse of dimensionality, difficult to visualize. So can we reduce this into the principal components? See, as the name suggests, principal component analysis. Given a high dimensional data or many features, you find out the important features or important components. Okay, if there are many components in that, you find out those important components and then project that into a lower dimensions, higher dimension to lower dimension. So that we call it as principal. Okay, principal means what? The major part or major component. Okay, so what exactly it is? PCA is a linear. So this is very important. Linear, unsupervised dimensionality reduction technique that transform high dimensional data into lower dimensional space while preserving maximum variance. See, this works on the concept of variance. So what is the idea behind PCA is, so it tries to find a new orthogonal axis called principal component axis that maximize the variance. So what is the idea here is, the variance contains the maximum information. Okay, so it contains the maximum information. So you find out those principal components which will give you more information, that is variance. So it helps in removing the redundancy. It finds out the particular information directions and then compresses the data. So that is the goal of your PCA. Now we'll see how exactly it does it. So we can do this in 5 steps. So I have given it in 5 steps, the principal component analysis algorithm or the procedure. The first step is data normalization. So what is data normalization? See, in a given high dimensional data, say there are 10 features and they have different samples for it, data for it. Now what happens, some data of some features may be strong enough or they may override the importance of the other features. So what is that you have to do is you have to normalize. That means bring them on the same platform so that our calculations and analysis will be accurate. Otherwise what happens, there will be a bias in the, if there is a bias in the data, then our calculations or accuracy will go down. So what is that you have to do here? So to prevent the scale dominance, okay, one feature may dominate the other feature. So for that you normalize everyone on the same platform or at the same base level. How will you do that? So you directly use your standard normal distribution, that is 0 mean and variance as 1 or standard deviation as 1. So it has 0 means and unit variance. Then because you are capturing the covariance, that is the variance in each of the component or the feature, we need to devise the relation, okay, relation between the variances among the different features. Okay, so that we call it as, we calculate it using a covariance matrix. For the given data set, you calculate the covariance matrix, compute the covariance. Why we need it? Correlation between the features. So you need to find correlation between the features. So that is captured in your covariance matrix. Then once it is done, then it's a part of the matrix and linear algebra concepts. How you are going to reduce it. See, the goal of matrix and linear algebra, I have explained in my video lectures also why we need all these things, why we are learning all those things. So basically to reduce the dimensionality of the data, we need the linear algebra concept. So one of the important concept is eigenvalues and eigenvectors. So check out my video lectures. I have explained like how they are helpful in reducing the dimensionality. So you first do the in step 3 eigen decomposition. That means you find the eigenvalue for this normalized covariance matrix. That means find eigenvalues and corresponding eigenvectors. So why? Because the eigenvalues and eigenvectors gives the direction in which the variance is maximized. Okay, that is the reason why you find the eigenvalues and eigenvectors. Then you select out of those eigenvectors, means eigenvectors actually gives you the direction. Okay, direction of the maximum variance in that order, and lambda value, that is your eigenvalue, will give you the variance in that particular direction. How much variance is given by scalar eigenvalue, and then the vector gives you the direction in which the variance is maximized. Then out of those different vectors or different directions of and the variance values, you select the best ones. That means you select the principal ones, highest maximum or highest variance that the vector that gives, you select that vector. So that you can capture most of the variance. That means some of the variance which is not required or it is a noise, you can ignore it. So this forms the principal components. Those eigenvectors, top eigenvectors, okay, in your entire decomposition gives you the principal components. Then one, that is you found out your top vector or principal components, you just transform into the lower dimension. That is project that the direction, the vector onto the lower dimensional subspace. So that is if you find the new coordinate system, project the data onto the principal components. So that is the 5 step for doing the principal component analysis. So now we'll see how exactly we will do it. Okay. So let us take simple mathematical intuition and then try to, with an example, try to solve the system. Okay. Now let us assume that let's have say D features and n data points. That means what? I have D features and then each feature has n samples. That is the meaning. So if I represent it using a matrix, let us say X, capital X is a matrix. I represent it as this. So let the J variable indicates the dimensions. So from 1 to D. Okay. And say I indicates the sample size 1 to n. So this means X1, 1, X12. These are the values. Say up to X1D. I will tell you what exactly it means. X21, X22, so on up X2D. Similarly up to Xn1, Xn2, Xnd. That means what? Each column or vector you see here, each vector is one feature, and this indicates the row values indicates the values in that. Okay, the vector. So this is a feature 1. This is feature 2. So on up to feature D. So there are D features, and each feature has n samples. Each feature has n samples. This is how I represent my matrix, the data into matrix, the features and the samples. So J indicates what? J is equal to 1 to D indicates the features. Okay. So for example, X1, X2, X3 to XD features. Then I indicates from 1 to n is number of samples for all j, right? So how I write it is xij. Each value I represent it as xij. So that means, for example, if I say x2, 3 means what? I am referring to x2 means the second feature and the third sample point in that. That is the meaning how I represent in the matrix. This is important to understand. Okay, so let's take an example side by side to understand it in better way. Suppose say that I have given a data of 4 persons. Okay, 4 persons, say P1, P2, P3, P4, 4 persons, and 3 features for each person, that is his expense amount, and then his age and rating. These are the 3 features. So I have P1, P2, P3, P4. So let us take some values for this and represent in the matrix form. So let's say 300, 250, 400, 350, 27, 30, 25, 28, 4.5, 4, 5, and 4.8. What exactly this means? See, observe this matrix here. So this is my say X. So this indicates the number of samples. Okay, 4 samples. 4 persons means 4 samples. So n is equal to 4. Okay, so this I is from 1 to n, 4. I equal to 1 to 4. How many features are there? D is equal to 3 features: expense, age, and rating. So for each feature I have 4 samples. That is the meaning. So this is how I represent my matrix. Now let's start with our algorithm. In the step 1, what is that we do? First step is data normalization or standardization. So what is that I have to do here? Convert this given matrix, okay, to a standard normal distribution. Okay. How will I do this? So for that I know already how to convert into a standard normal, that is using z score. Z equal to, the random variable x minus mu by sigma. So for each of this feature I have to find mu and sigma. So how will I find it? So I already know mu. So I will write for each feature mu j. Mu j means what? This. For each feature I am finding the average. That means for each column I am taking the average of each column. That is the meaning. X mu j equal to. How will I calculate it? I will calculate it as 1 by n. You already know this summation I equal to 1 to n x ij. So x ij means, so for j equal to 1, I am selecting x 1 1 x 2 1 x 3 1 up to xn1. This is this column. So I am finding the average of this, the entire column. Okay. So what I will get if I take this, for example, mu 1 2 3, mu expense, mu age, and mu rating. I will write it as a simple one vector. So I will get it as, using this formula, I get it as 325, 27.5, and then 4.75. Is the average of this column is 325. The average of this column is 27.5. The average of this column is 4.75. Now you similarly find the standard deviation. How will you find this standard deviation? Sigma j is equal to, you already know, the root of 1 by n sigma I equal to 1 to n x I j minus mu j whole square. This is the formula you know. So that means standard deviation for each of these columns, or that is each of the vectors. So mu vector I will write directly, sigma vector is equal to, we'll get it as 64.55, 2.08, 0.376. Okay. Now you convert it into standard normal. So how will I convert standard normal? Z ij is equal to x ij. For each of these values, you get the z score using this formula, that is standard normal, x minus mu j divided by sigma j. Then you will get a z matrix. So this x matrix I am converting into standard normal. Why I am doing this? Because here the first step, normalization is required, because for example expense, the values are 300 to 50. They are very much scaled compared to rating and age. So when I calculate, they should not have an effect. The values should not have an effect on the your final results calculation. So they have been scaled. So if you convert everything to normal, so everything will have zero mean and standard deviation. Zero mean, standard deviation, each feature. That means what? They lie on the same platform now. So each of them will have same z score. That is, base is zero mean for each feature and standard deviation is 1. So I calculate this z matrix. So I converted the x matrix to z matrix. This is the normalization first step. Z12 up to Z1d, Z21, Z22 to Z2d, so on. So we'll have Zn1, Zn2, Znd. Okay, now you observe the important thing here is, what is the size of this matrix? So it belongs to real domain. So I have n samples and d columns, d features. So n cross d. So if you observe here, this also belongs to real numbers. So I have n samples and d. This will play an important role when I do the projection. So for this example, I will get this z scores minus 0.39, minus 0.24, minus 2.0, then I have minus 1.16, 1.2, minus 1.53, 1.16, minus 1.2 plus 1.13. We'll have last row as 0.39, 0.24, and 0.60. So basically what I have done here, to convert this X matrix, that is normalize it to convert it into standard normal Z matrix. That is the first step. Why I am doing normalization? Again, I'll repeat. Each dimensions, there are multiple dimensions here. So one dimension scaling effect should not have the impact on the results. So you convert them into on the same base, that is standard normal, and then convert into Z matrix. Okay. Now we'll go to second step. Step 2 is actually important. This is where actual PCA starts. You find the covariance matrix now. Why we need covariance matrix? For each feature, we need the correlation among the other features. Okay, that is given by our covariance matrix. So you already know covariance matrix is given as, check out my video lectures on covariance matrix. I explained how we get this. Is equal to, so C with the covariance matrix for our Z matrix. So you get it as Z transform into Z. Okay, Z is the normal matrix already we found out. So this give the covariance matrix. So for our example, we'll get the covariance matrix as C is equal to 1 minus 0.92 minus 0.20 is minus 0.97 minus 0.92 1 minus 0.89 0.97 minus 0.89 and 1. So what exactly this means? So observe here, this size is what? Okay, this size is n cross d. Okay, this size is n cross d. Sorry, d cross d. Why it is d cross d? See, covariance is between the features. So for example, here it is my expense, this is my age, and this is my rating. Here also same, expense, age, rating. This is the covariance matrix. Expense to expense covariance means what? The relation is 1 because they are the same features. Expense with age is minus 0.92. That is how they are related. Expense to R, that is rating, is minus 0.97. That is what is the correlation between the pair of features. That is the covariance matrix, right? So you are understanding how they are related so that I can find the actual principal component. So this, if you observe, it's a 3 cross 3 matrix. That is, so number of dimensions matter. So 3 cross 3. Now C is a 3 cross 3 matrix. Now if you observe, two key points here. This is always a symmetric matrix. The covariance matrix I get here is symmetric matrix. If you observe in this example also, so 1, 1, 1 is the diagonal elements, minus 0.92, minus 0.92. So if you hold along the diagonal, I'll get the same elements. The mapping is 1 to 1 here. So it's a symmetric matrix. And the second point is, it is positive semi-definite. So check out my video lectures on vectors and linear algebra. What exactly it means? For this covariance matrix, the eigenvalues are always greater than or equal to 0. Okay, semi means greater than or equal to 0. If it is positive definite, always greater than 0. Positive semi definite means greater than or equal to 0. So eigenvalues are what I get for this matrix are always greater than or equal to 0. Now you find out the eigenvalues now and eigenvectors. Why I need to find eigenvalues and eigenvectors? Okay, I want to find the principal components. For that I have got my covariance matrix. So eigenvector, say V, let us indicate it as V. It gives the direction of variance. Okay, my lambda will give the variance value. That lambda is a scalar, this V is a vector. Okay, eigenvector gives the variance direction of the V, gives the direction of the variance. That is the, it gives the principal axis, different principal axis it gives. Later we'll select which one is the best. Okay, so why you find eigenvalues and eigenvectors? Eigenvector will give the direction of the variance, that is the principal axis, because we are trying to find those directions and the value where the maximum is maximum variance. We have a maximum variance. So lambda will give that variance value and we will give that direction. That's why you find out the eigenvector. Now you already know the procedure how to find eigenvalue. Determinant of this matrix C minus lambda I is equal to 0. You evaluate this and then you get the eigenvalues. So eigenvalues are always positive semi-definite. So that means we'll get and arrange them in this order. Okay, decreasing order. Lambda 1 is greater than or equal to 2, 3, so down up to lambda. How many lambda values I'll get? See, because the d-dimensional 3 cross 3 matrix, right? So square matrix. Then only you can find the eigenvalues. So there are d eigenvalues. and all the eigenvalues are greater than or equal to 0. They are semi-definite. And you arrange the corresponding eigenvectors. You know already how to find the eigenvectors. For each eigenvalue, you find an eigenvector and then arrange them same in that order. Okay. So v1, v2, v3 for corresponding lambda. Okay. So now already know this each vector, this each eigenvector will give me the direction of the principal axis. Okay. And then lambda will give me the variance. So when I arrange them in the decreasing order, that means what? The first eigenvalue will give the maximum variance and the direction in which that variance is that is the principal axis. That's what you have found out. That is what is the core of your principal component analysis. You already found out the principal axis. Now, so for this example, if I take c minus lambda I equal to 0 determinant, this implies I will get lambda 1 equal to 2.84, lambda 2 is equal to 0.14 and lambda 3 is equal to 0.02 because there are 3 cross 3 matrix, so dimension is 3. So I'll get only 3 eigenvalues. The corresponding eigenvectors I'll get it as v1 equal to 0.58 minus 0.56, 0.59. v2 is equal to 0.40, 0.83, 0.39. v3 is equal to minus 0.71, 0.01 and 0.71. The next is step 4. Step 4, you choose the best or top k eigenvectors. Okay. So how will you choose this k? For example, say that I have got it, there are 10 dimensional features, I got 10 eigenvectors. So how many are principal component analysis? I need some k, or k is equal to 5, 6. I have to choose some top eigenvectors, that means which have high variance in this order. That gives my projection matrix. Okay. How will you calculate this k? You can go for some cross validation techniques for the data and then find out what's the best value of k. So using those top vectors, we will take our final projection vectors, because using this vector only, I need to project my data onto the principal direction. So I'll say v1, v2, vk. I have selected k vectors out of d vectors, d eigenvectors. So what will be the size of this? This is belongs to r d, okay, into k. So there are k columns and d rows. v1 has d values, right? Because it's a d-dimensional. Now, once you're done, so I got this W. W will give me the projection vector or projection matrix. So I have to multiply with my Z. Okay, that is the normal matrix, initial data matrix, normalized data matrix to get my new projection line. Okay. So how will I find out? So for example, say that we can find out the explained variance in each lambda, each eigenvalue will be given by that particular eigenvalue divided by sum of all the eigenvalues. For example, say that here, let me take variance explained by lambda 1 will be equal to what? 2.84 divided by sum of all these values. It will get as 3. So this is almost equal to 94.6%. That means what? This only one variance is the major one here. See, if you compare all these are very small compared to that. That means what? This is the major principal component. The vector corresponding to that eigenvalue is v1, which gives the direction in which I have to project. That is the meaning. That's why I have chosen those k values here, v1, v2, top eigenvalues vectors. Okay, that is the meaning here. So you can calculate what is the percentage of variance explained by each of these eigenvectors, eigenvalues. Okay, so you choose top of them. Top. How many you want? K values. Okay. So in this example, let me take k is equal to 1. So my projection matrix or vector will be only v1. Okay, v1. So this is nothing but v1 is 0.58 minus 0.56, 0.59. The last step is a simple one. You project. You have obtained everything now. Just project to the lower dimension. So projection. So you already know the projection concept. So I have the new dimension y for the principal axis. So how will you z into w? So z is the initial normalized matrix, the data matrix, and then w is the projection direction. W gives the projection direction. Please check out my LDO video lecture, linear discriminant analysis. I explained how actually this projection works, and also my matrix and linear algebra I have pinned in the description. How actually the projection, how you can visualize this projection. I have given a detailed picture. Okay, so now this is my final projection. So if you observe, y will be, the size will be what? The z is n cross d, w was d cross n, right? So it becomes n cross, sorry, this was n d cross k, n cross k. This is the reduced. See, what was initially my data vector? So x was d, sorry, n cross d. So I reduce it to n cross k. Okay, that is the dimensionality reduction. So from this I reduce to dimensionality. So for our example, so y will get it as z into w. So y will be final minus 0.21 minus 2.25 2.01 then 0.45. So if you observe here, this is size is 4 cross 1. That is n is 4, k is I selected as 1. That's the final projection. So I am projecting it in only one dimensional. See, this is only one dimensional. So converting my 3-dimensional, initially the data was 3-dimensional, I converted into 1-dimensional. So I have reduced the dimensionality. That is how the principal component analysis works in 5 steps. So if you observe here keenly, for the same example, I have given the dimensionality reduction. So initially it was a 3-dimensional, so it written a cube. Okay, expense, age, and then rating. So the points are represented like this, 4 samples. Now this 3D, I reduce the dimension to 1 dimension using the principal component analysis. You can easily visualize and see it here. So and also it gives the major principal axis. This is the principal component in which I am selecting and projecting. Okay, PCA projection. So P2, P1, P4, P3. Now, so I can just compare easily with the singular values. Okay. So what is the impact of each of these samples and features? So that is all about principal component analysis. Hope you enjoyed this video. So there are some more limitations of PCA. To begin with, so you assume that PCA is linear and cannot capture non-linear relationship. This is one of the major limitation. Okay, PCA is the linear projection. Okay, linear projection cannot capture non-linear relationships. Covariance matrix is capturing your linear relationship. PCA ignores class labels, so it's unsupervised machine learning. So maximum variance may not give the best class separation always. PCA causes information loss by discarding low variance but potentially important features. Sometimes what may happen, even if the principal component basically selects the direction with the maximum variance, but some features may have low variance and then they may be of importance. That may be ignored sometimes because it always selects the direction with the high variance. PCA is sensitive to feature scaling and requires proper normalization. Principal components lack interpretability since they are linear combination of original features. So linear combinations is the biggest limitation of principal component analysis. Hope you enjoyed this video. Thank you for watching. Please like, subscribe and share. We'll solve many problems on this concept.